the word quantum, that sounds really kind of like sci-fi and intimidating, but it's not anything to be scary or scared of, excuse me. So let me help you out with that. So Max Planck, he was a German physicist, and he hypothesized that if something was radiating or giving off energy, it would be in these discrete units. Now, I see the word discrete a lot in daily life, and it's a word that I use a lot. Does anybody want to share with me what that word means?
Separate, distinct.
Yeah, so, and I like, if you're ever in an argument with somebody, right, and they're like, you're trying to make a point, and they're trying to make a point, but what they're bringing up has nothing to do with what you're talking about. Like, it sounds real classy if you're like, you know what you're discussing is a discrete issue from what I'm trying to propose. And so, like, you just sound real classy, right? So go for that. But discrete means separate, right? It's its own little separate issue. It's not connected. It's not part of what you're talking about. It's like a little chunk of something off to the side. That's almost kind of where I go in my mind. It's not related. It's separate. Okay. And then here's a crazy word, quanta. Take a minute at your table, talk to your group, and talk about what the word quanta sounds like. Take a minute. Go. I'm gonna pick one of y'all. Yeah. Hello. All right. So, what did you guys get at your table, Lucy? Yeah, sure. It sounds like quantity. So this is quantity. So when we're talking about energy, we're talking about these separate quantities of energy. So quanta is kind of where we're heading with this. And so when we talk about quantum physics or quantum mechanics, they're really just talking about little chunks of energy that are separate. So that's really not that scary, right? And so let me kind of tie this back to our warm-up. I had asked you guys what was the difference between a ramp, if you're going up to a doorway, and some stairs. And so we had kind of decided that when we're on a ramp, we can be anywhere. We can stand there and be there for a long time, anywhere on this ramp. But if we're talking about stairs, really, you can't be between the stairs for very long. So we've been talking about all these electrons and how they get excited, they go up and then they come back down. But when they go up, they stay on an energy level. And when they come back down, they rest on another energy level. And so the reason why we have n equals 1, n equals 2, n equals 3, all these distinct lines when we're talking about this Bohr model and these energy levels is because energy is gained and lost in these quanta. So see how that looks similar to my little Bohr model? The electrons never hung out in the middle. That ain't a thing. So this ain't a ramp. We're talking about some stairs. Okay. So these discrete units are called quantum. And so when we're talking about bacteria or quantum, so that single word is like bacterium. That single quantum is 1. And so multiple is bacteria or quanta. So that's just good like science words for you. I don't know if you were looking for a vocab lesson today, but that's kind of like why it's going back and forth between the two words that sound the same. It's the same thing. Quanta is multiple, quantum is 1. Okay? So anyway, so the height of each step is equal to 1 quantum of energy, and so energy again can only be gained or lost in these chunks, these quantum. And this is not even something that we're going to spend a lot of time on. This is something that we'll do in AP Chemistry, but the energy of this quantum is equal to this guy, Planck. He figured out this constant. He actually piggybacked off of the work of Einstein and came up with this constant. He had worked with electrons coming off of metals and stuff, photoelectric effect. I'll show you a picture if you're curious. But anyway, times the frequency. Remember, the frequency of light is tied to the amount of energy. So the amount of energy is this crazy Planck's constant times the frequency. And so if you're just curious, I'll show you real quick. Basically, this photoelectric effect, Einstein, that's why he won the Nobel Prize. I don't know if, did you know that? He figured this out. And that's pretty cool, right? And so, had this little metal plate, and you know, you could shine light on it, but only at a certain frequency would it start to like send off these electrons. And so there's more to it. Anyway, we don't need to go into that. I'm not trying to blow your mind today, but that's the first part. Second part that I want to talk to you about is the emission spectrum. So this is tying back into what we've been discussing. Just a second ago, I drew up for you guys. I drew up for you on the board the electromagnetic spectrum. I drew mine going the other way. I had started with lowest energy to highest energy, so mine was the same drawing. But when I did mine, and I did that on purpose, when I did mine, I had radio waves being over here. And so I drew mine from lowest energy to highest energy, or lowest frequency to highest frequency. Look at this. This is wavelength. Lowest wavelength to highest energy. Lowest wavelength to highest wavelength. And so the longer that wavelength, you know, the lower the amount of energy. And we have talked about that quite a bit. So anyway, same stuff. There, that is the Greek symbol for gamma, in case you're wondering. So there's your gamma rays and your X-rays. There's the aliens coming in. Just kidding. There's ultraviolet, infrared, microwaves, and radio waves. And so there you go. People are worried about microwaves giving you cancer and stuff. They're actually lower energy than heat or visible light. So they do certain things to water molecules and make them rotate. That's how that works. The water molecules rotate because they're polar, and that's why your food warms up, because it like rubs them together, like your hands rub them together. Okay, I'm getting a little too much into this, but it's super interesting, right? That's awesome. I know, it's so cool. Anyway, so there's my spectrum of light. What's going to happen, and this is what we're going to do in the lab tomorrow, I'm going to take and put those emissions tubes, that's a little crazy looking long light bulb, in the little light source, and you're going to use your spectroscopes, which are going to act like a prism. And what's going to end up happening, and we already did this, I like to show you before I show you, because then it makes more sense when I explain it. It's going to take these single colors of light, and it's going to split them up into their individual components. And these three wavelengths of light are due to those electrons falling. This one would be falling from something like we had the n equals 5 to n equals 2. This one would be something more like maybe 4 to 2. This one would be like maybe 3 to 2. So that should tie into what we just talked about. You should feel pretty comfortable with that. How you feeling about that? If you're not totally with me, I'm going to get you a draw here in a second. But this ties back into, like I said, what we were discussing. So here's hydrogen's emission spectrum. This is exactly the same as what we're using. This doesn't change, okay? And so somebody asked me in first period, Ms. Freeman, can I look this up somewhere and see these barcodes or fingerprints for each element? Absolutely, and it's well known and documented. So, and this is what people like astronomers use to detect what is in stars. And people on Earth, for Earth reasons, use them too. But so that's the emission spectrum for hydrogen. And I need to mention just real quick, light acts like a wave, but it also acts like a particle. And so if you happen to have a particle of light, if I have a quantum of light, it has a special name. Notice this was not in your PowerPoint. You need to write that down. A quantum of light is called a photon. And the photon is this particle of light. So in the world of quantum physics, there's this whole, it's underlying theory that kind of drives the whole thing, that light acts like a wave, but it also acts like a particle. Pretty cool. And these particles of light are just called photons. And that really is easy to remember, because when we talk about photo or photosynthesis, those are all coming from the same word for light. So that's that. Are you okay with that? It's just a special word for particle of light. And so when you start to study chemistry a little bit more in depth, you start to talk about how these photons, those are really can be viewed together with electrons and how that comes together. Pretty neat, but I think that's where we can stop with this. What I want you guys to do, that's this side of the paper, right? If you flip your paper over, I left a little space in the bottom right-hand corner blank, and I would like you to go through this with me, and I would like you to draw in this Bohr model, and it goes from n equals 4 all the way down to n equals 1. So draw this in for me. You don't need to talk. Please don't. There's your nucleus if it makes you feel better. I'm going to get you to draw this. I don't want you to draw the colors in quite yet. I want to make sure that you watch and listen as I explain that one more time.
No.
Alright, so you should have 4 concentric circles. And so put your pencils down and don't draw anything. Just watch, okay? So if you look, what I have here is I have an electron. It's going from n equals 1 to n equals 2. That's going from ground state where it hangs out normally. Ground state's it's like lower energy stable state to an excited state. So n equals 2 is excited state. It's not going to stay there forever though. It's going to come back down. When it comes back down, it's going to release light. And that light is pretty low energy because it only went down 1 level. So that's red. This is what I was talking about a minute ago. Alright. So let's look again at a different one. This electron, its ground state was n equals 1 and it went to n equals 3. So I should expect to have a higher energy, maybe, you know, green, or not green, maybe orange or yellow, or green. So I've done this PowerPoint today, so it is green. So n equals 3 to n equals 1 is going to release green. So this one is going all the way from 1 to 4. So this one should be pretty high energy. And so here, when it comes back down from n equals 4, see, all the way to n equals 1, then I'm going to get violet. This last one is going from n equals 2 to n equals 4. And when it comes back down, it's going to release blue wavelengths of light. And so these wavelengths of light that we see, those are photons. Okay, and then what color they actually are based on how far they fall. How do you feel about that? Feeling good? Okay, so now you can draw these in for me, and then we'll talk about your polyatomic ions. So go ahead and get started on that for me.